Good evening, everybody. Tonight we're going to talk about counting some more. So we've been doing counting all semester. We've been counting how many rows we have in truth tables. We've been counting how many elements we have in a set. We talked about the Inclusion-Exclusion Principle where if we had two sets and we took the union, we had to find out how many elements were in the set. And it would just be adding the size of both sets except for what? Except for the overlap. So we would have had to subtract the intersection. So that was one of the rules that we've used. So let's mention it again. It's called the union rule or the Inclusion-Exclusion Principle, depending on where you look. So that was, if I have two sets and I take their union, then the number of elements in that final set is adding my two original sets and subtracting, the intersection. So the stuff that's in both of them. And the reason for that is that because A intersect B is a subset of A, right? And it's a subset of B. So when I add these two things together, I'm actually adding those things twice. So I have to subtract them once. So that I only count each element just once. So what's an example of a problem where I might need to do something like this? Like a problem like count the number of people who have something.
Flippers?
Well, it has to be something like a union, right, in order to have to use this. So count the number of people who have flippers.
And antenna.
And antenna? Or. A union is an or, right? So count the number of people who, and I'm going to put the word either in there, or who have either flippers or antenna. So if we were doing that, first we would count that would be what? Flippers, union, antenna, right? If F were all the people with flippers and A were all the people with antennae, then in order to count that set, I could use the number of people with flippers and the number of people with antennae to count the union, right? So that would be the size of the first set plus the size of the second set, subtract the size of the intersection. So an example of a problem like that where we have to count things all the time is, say, how many students are either computer engineers or computer scientists in North Carolina State University, because we have a lot of the same classes and resources that we use. So sometimes you might want to know how many students are either or, right? So you might want to say, okay, how many CSC are there? Union CPE. And some people double major, right? So if they weren't allowed to double major, then this would be a simple case of adding. So this would be equal to the CSC students plus the CPE students minus the people who are both. I mean, a similar kind of question would be how many people in this room have either brown eyes or brown hair? They could have both, right? So I would count all the people with brown hair, count all the people with brown eyes, and then subtract the people who had both, because I would have counted them twice. Okay, good. So that's one rule that we use. There's two main rules you use when you're doing counting. And the other rule we've used all semester, and that's called the product rule. So when we were counting truth tables and how many rows were in a truth table, how did we do that? First, we counted the number of variables we had, right? And how many possibilities each one had. So say we had P and Q and we had to make the truth table for that. Then we have two variables. So that's two blanks. Each one of them has two possibilities. P can be either 0 or 1, and Q can be either 0 or 1. And since I have to list P and Q at the same time, I multiply. So whenever I have an AND, if you're noticing a pattern here, if I have an AND or an intersection or something, I'm going to multiply, just like we've been doing all semester. Whenever I have an OR, I'm adding, except for in the case of sets, I have to subtract intersections. So if I were to say how many people have brown hair and brown eyes, then I would, that's a little bit different. That's not quite the same thing. That's a different problem. That's an intersection, right?
Yeah.
So this is two independent things. So these are independent.
Move up.
So P and Q are independent in this problem. And anytime you use the product rule, you should have independent things. Because if P were to somehow depend on Q, then I would be counting more things than could possibly be there.
Like male, female would fit there, right?
If I wanted to say, if I have two committee members, and each one of them can be male or female, then this would be the number of ways I could distribute them, right? I could have male, 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 female, female, male, and female, female. There would be 4 ways. Because I would have 2 ways for the first one and 2 ways for the second one. Right?
Yeah, but you can't get intersection. I was thinking of a case where you can't get intersection. You can't get one who is both male and female. And therefore you love
now, independent, okay, independent is different than what you're saying.
Oh.
Like I could have different sets. Like this could totally be, like this could have letters and this could have numbers. Or this could be words in the English language and this could be numbers again, or it could be people, or it could be anything. These are things that don't depend on each other. But if things depend on each other, if you can ever make some kind of implication relationship or something, if that's always true, if this is a logical implication, then Q's values depend on P. But still counting the rows in the truth table is still going to be the same. But if I were making a problem that, I was counting times that P happen and Q happen, actually, really, I only want to count each one of them. Let's not go into that. That's too abstract. So let's do some problems here. So let's take some problems. So a simple example of the product rule is how many rooms are in a building with 30 floors and 5 rooms per floor. So you have to ask yourself questions when you see counting problems. First, whenever you see how many, you know it's a counting problem. You see that there's an and, so it probably uses the product rule, especially because the rooms and the floors are independent. Every single floor has 5 rooms, no matter what floor it is. So that's independent. So I could draw a picture of this. Like if I didn't know the product rule, I could draw a picture and count it. And this is the kind of thing I want you to get in the habit of doing when you're doing problems where you have to count things. You should draw a picture, just to make sure that you're counting it the way you think. Sometimes you might count something and make an assumption, but if you were to draw a picture, you would realize that your assumption is wrong. In this case, it's kind of a simple problem, right? I would have a building, kind of lopsided. And on each floor, there's 5 rooms. So even without knowing the product rule, I would look at this and go, okay, I need to add 5 and 5 and 5 and 5 for every floor, right? So 1 up to 30, that would be what? The summation, just to torture you for a second. K equals 1 to 30 of 5. That would be 35s added together, right? Which is equal to 30 times 5. because I have 30 floors, 5 rooms each, so I would multiply those to find out how many rooms total. Okay, let's do another problem. We've done a similar problem to this before. So how many numbers, integers, in the set 1 to 100 are divisible by 2, 3, or 5? So we see the word or, and we immediately think this is probably an inclusion-exclusion or a union rule problem. So I need to count the size of each of the sets independently, and then I'm going to have to take out the intersections. But this isn't just 2 sets, it's 3, so we have to use the more complicated rule, right? So that was A union B union C is the sum of all the individual sets, subtract all of the intersections, and then do what? Then we have to add the triple intersection. I had to add it back because we subtracted all of those out. So this fixed all the overlaps of these sets, but it actually took out that the middle point if you were looking at the Venn diagram. Okay, so we would count, so these will be the numbers, A will be the numbers divisible by 2, B will be the numbers divisible by 3, and C will be the numbers divisible by 5. So A is equal to what? How many numbers divisible by 2 are between 1 and 100?
50.
There's 50, right? How about numbers divisible by 3? 33. How about numbers divisible by 5? 20. So do you guys remember those tortuous floor and ceiling functions that we used? Okay, they're tortuous only because you have to use them for stuff like this, right? Because this number is actually equal to 100 over 2, the floor of that, right? All of these are floors. This is 100 over 3, the floor of that. Because there's 100 numbers, and every third one is divisible, but it's not evenly divisible by 3, so we have to go back down and round it down because we can't get to the next number after 100. So that's what we use these floor functions for, is usually because of counting, because we only want to count whole things and not parts of things. And this is a lot faster than listing all the numbers that are divisible, right? So the ceiling and floor functions are really useful for making things integers when we want to count whole things. Okay, so for this problem, I need to add 50 and 33 and 20, right? But then I have to subtract A intersect B and all that other stuff. So now I have to figure out what those are. So A was the numbers divisible by 2. So it goes 2, 3, 5, A, B, C. So let's figure out A intersect B. A intersect B is what?
Divisible by 2 and 3.
So these are numbers divisible by 2 and 3, which is also equal to the numbers divisible by 6. So this is the numbers divisible by 6, which is the floor of 100 over 6, right? And that would be 96 over 6, which is 16. So A intersects C is, that's the numbers divisible by 2 and 5, right? So, and the least common multiple of those is 10. So that's all the numbers that are divisible by 10. So there's 10 of those between 1 and 100, right? 100 over 10. And then B intersect C is the numbers divisible by 3 and 5. So that would be the floor of 100 over 15, which is 6. And then the last thing we have to figure out is A intersect B intersect C. So that's the numbers that's divisible by all three of 2, 3, and 5. So that's numbers divisible by 30. And there's only 3 of them. So our final answer is going to be, because we had size of A was 50, so A union B union C, numbers divisible by 2, 3, or 5, is 50 plus 33, because this was divisible by 2, divisible by 3, plus 20, that was divisible by 5, minus 16, that was numbers divisible by 2 and 3, minus 10, that was 2 and 5, minus 6, that was 3 and 5, but then we have to add the 3 back that are divisible by 30. Now, I don't mind on a test if you don't actually add these numbers up. If it's really clear to me that you know what the steps are and you do the subtraction and addition like you need to, then I'm assured that you can either use a calculator or figure it out correctly. Okay, but how many numbers is that? Just
101.
101 numbers. It can't be 101, can it?
3. I'm sorry.
Can't be 101 because we only have 100 numbers, right? So we have to have, that's 53, minus 16 is going to be 40, minus 3 is 37, minus 10, 27, minus 6 is 21, plus 3 is 24.
Plus 50.
Plus 50.
Did I mess up?
You missed the first bit.
Oh, 103. Okay, so 74?
24.
That's a lot of numbers, isn't it? So now you guys see why I'm lenient on addition, right? Just look right over the numbers I need to add. Okay, so this problem is in your notes on page 3 of packet 6. So you can take a look at it. It lists actually the sets that are in there. Page 3, if you have the new copy, it's page 3 of packet number 6. Okay, so let's do some other problems. Can anybody think of anything they'd like to count that we might actually be able to count right here? Okay, so let's do some other kinds of problems, not necessarily these. How about how many ways are there to roll a dice 10 times in a row? Okay, so how many possible sequences of numbers could you have if you roll a dice 10 times in a row? Let's write that down. Roll a die. So how many possible sequences are there for rolls? So again, this is a case where I would draw a picture and then figure out what happens in each part of the picture. My picture would be, I would just put down a space for every number that I would write down that I rolled. So I'd say, okay, this is roll number 1, roll number 2, 3, 4, 5, 6, 7, 8, 9, and 10. They always get closer together at the end, somehow. Okay, and we have a 6-sided die. So how many numbers are possible on my first roll?
6.
There's 6 numbers possible there. How about on the second roll? 6 again, because I don't exclude the one that I rolled the last time. So that happens again for all 10 of them. So and this is something where all of these get ANDed together because I do the first one, then I do the second one, and I do the third one in a sequence, and they're independent rolls. So I multiply them. So this is 6 to the 10th sequences of rolls. Now in this case, if someone asks you, does order matter? What do you say?
Not in this question.
It does matter. Because say I just looked at the first 3, right? Getting 115 is different than getting 511. Because it's counted. Each of those different things is counted one time, right? The 1 is counted once in this 6, a 1 is counted once in that 6, a 5 is counted once in that 6. So all of those orders are combined. So order does matter in this case. If I can number my blanks, then order matters. So if it makes a difference which one I rolled first and which one I rolled second, then order matters. And if you see sequence, it's going to be order matters unless something in the problem tells you to ignore what order they are. It's really natural for us to do things in sequence because we normally can only do one thing at a time, right? Pretty much. But you may do lots of things simultaneously, but you really only can do one at a time and rotate, which is really what a computer does too. So our natural thought is to think of things where order matters. So whenever we do things where order doesn't matter, we actually usually have to divide out the order, and that's what we're going to do next. So this is a permutation. And I told you last week I would tell you what replacement was all about. Permutation is because order matters. And this is with replacement because I was allowed to use the same number over and over again in the sequence. So that's what replacement means. Like this first one could have 1, the second one could have 1, all of them could have 1. I didn't toss out the 1 just because I used it one time. So that's what with replacement means. So this is a permutation with replacement. So there's no button on your calculator that will do this, permutation with replacement, because it's so easy to draw the picture and figure out that it's 6 to the 10th, and you can just use the power button on your calculator. Yes, Sal?
What if you had to roll the die 1,000 times? Wouldn't you run out of different types of sequences?
Would I run out of different types of sequences? If I had to roll it 1,000 times, I'd have the same picture 100 times.
I'm sorry, I'm confused.
So I would have, if I had to roll a die 1,000 times and I want to know how many sequences there were, every number in the sequence would be a 6 possibility roll. And there would be 1,000 of them, so it would be 6 times 6 times 6, 1,000 of those. Does that make sense?
Yeah, I wasn't thinking.
Okay, so if I weren't using replacement, I couldn't do 1,000, right? So if I wasn't allowed to roll any more ones again, so say you were rolling the die and somebody said, you have to roll this many different numbers. How many times could you roll?
6.
6, except you might roll a lot tossing out ones, right? So if I rolled 1, then I wasn't allowed to get that number again. I'd have to keep rolling until I got a different one. But the sequence of different ones would only be up to 6 of them. Joni?
Yeah, how are you explaining the order mattering here? I didn't get it clearly. When you say the order matters in this.
This is a sequence. So if I can tell the difference between 2 roll sequences, then order matters. So like 115 is different than 511, right? That's what order matters. If those are considered different, if 115 and 511 are considered different, then order matters. If they're not considered different, like as if they're a set, then order doesn't matter. But I was saying our natural inclination is to say that order matters. Yes?
So, a similar problem where order didn't matter was, say, how many different combinations could you get if you roll the dice 10 times?
That's right. you would have a whole different wording of the problem. So I was trying to give you clues for when order mattered. The fact that we say sequence, how many different sequences are there, that's orderings. So if you see the word sequence or series or something like that, you know it's going to be a permutation where order matters. And what's your name, Kevin?
Van.
Yeah.
Van.
Okay, Van. Van said that if we were asked a different question, like how many combinations of numbers could you get if you roll this many times, that's definitely a problem where order doesn't matter, right? So it doesn't matter what order they come in. These would be considered the same if that was a combinations problem. So combinations are where order doesn't matter. So why in our truth tables does order matter? So why do we consider 0, 1 different from 1, 0 in a truth table?
Because different
Because the
variables
weights-
are represented.
That's right, because different variables represent different things, and I certainly don't want to just reverse them any old time. Okay? So it matters in there, and that's why we have 2 times 2 elements in our truth table. Okay, and we said what was with replacement again? That's where you're allowed to pull the same value again. So it's not tossed back into the hat. When you make another selection, you're allowed to use it again. So I'm using the vocabulary that people usually use when they're doing counting problems, and they talk about making selections and the set you choose from and how many you choose. Okay, so if we wanted to do the same problem, let's see. Let's just do another problem like that. So this question asks, how many strings of 3 letters are there? And I list the letters A to Z. So here again we can draw a picture. We have the first letter, the second letter, and the third letter. So how many choices do I have for the first letter? 26. How about for the second letter? 26. And 26 for the third. So this problem is 26 raised to the third. So we're seeing a pattern here. We have our number of choices. So number of possible choices, or the size of the set that we're choosing from, raised to the power of how many choices you make. So this is number of possible choices per choosing. So whenever I make a choice, how many possibilities do I have? And that this is how many total choices I made. And usually that's denoted n to the r. So n is the size of the set you're choosing from, and r is the number of choices that you make. I don't really want you to memorize this. And I don't want you to memorize this because as soon as you memorize it, you'll mix it up with all the other things that you memorize. And all the other counting things that we're going to be talking about have n's and r's in them too. Okay, so I'd like you to remember to draw the picture. And you only even have to start the picture. You don't have to have a whole picture. If it just reminds you which formula you have to use, then that's enough of a picture. So let's do another problem. How many ways So you're the photographer and you're trying to figure out which pictures to take, how many ways are there to take a photo of 6 people at a wedding where there's 10 people that you might want to take photos of, so like in the wedding party or something. The first thing you ask yourself when you solve a problem is, does order matter or not? If the problem doesn't make it obvious, you just have to write down which one you assume when you solve the problem. Okay, so you can take a vote and everybody do the same thing, or each person can decide in this problem whether order matters or not. Personally, I don't care what the order is of people in a photograph, so I would say this is a combinations problem. Some things you can figure out, like it might not say whether order matters or not, but if it's talking about giving out prizes, do you want to go to Hawaii or get the free Coke can? The order matters which prize you get. If you get first prize or third prize, it makes a big difference, right? So in some cases, you can just reason through whether you care whether you would come first or third. And if you care, then order matters. If you don't care, then order doesn't matter. And you just have to write it down. So I'm going to assume order does not matter. So this is a combination. And my set I'm choosing from is 10. So I choose 6 out of 10. Or C, 10, 6. Or 10, choose 6 is the way to read that. So this is what you would use on your calculator, but just now we're going to derive how we actually calculate this number. Because sometimes what happens is you use this button on your calculator and you put the numbers in and it says E, because these are factorials. And factorials get large very quickly. So in your homeworks, I'd rather see your answers in terms of either this formula or factorials, depending on what I ask you for. I may ask you for this. Just tell me if it's combination and how many you're choosing from. Or I may ask you for the factorials. For the most part, I do not want you to calculate what the number is. If I already know what the number is. I don't need you to tell me. I want to know if you know how to solve the problem. Joni.
Can you write 10C6 instead of C10? 10 first and then C6. Is that a legal way of representing combinations?
You mean like this?
Yes.
It's kind of legal, but it's a little confusing. Like, this is the normal one that we use. The top number is always the number that we're choosing from, and the bottom number is the number that we choose. And the reason why that is done that way is because we also have the permutations like that. So this is traditionally how it's written, and after you use it for a while, it'll make sense to you. Okay, so we started solving the problem. We know what kind of problem it is now. We just have to figure out how to finish. Okay, so we know what order doesn't matter, but I also said before that we only can do things in sequence. So what we're going to do is do it with order, and then we'll take it out, take the order out. Because you can only pick one thing at a time, generally. So what I'm going to do is I'm going to make 6 blanks for the people I'm going to take photos of. So there's 6 of them. And the order matters, notice, I can number the lines so order matters. If I draw lines in the first place, it usually means order matters. So I have a set of 10 people I'm choosing from. And they're going to go into these R blanks, right? So how many choices do I have in the first position?
10.
How about the second one? So immediately, this is a without replacement problem, right? Because I can only take, unless you have some fancy photo equipment and a lot of time, you only get to take a picture with one version of one person in there. So you can't use the same person twice in a picture. So the next time we have 8, 7, 6, and 5. So this is just like doing a permutation of 10 things taken 6 at a time, which was 10 factorial over what? Sorry, 4 factorial. we have to do 10 minus 6, right? So it's actually 10 factorial over 10 minus 6 factorial. So, but we didn't have to memorize that because we can use our blanks that we have. And see, that's 10 times 9 times 8 times 7 times 6 times 5. That looks just like 10 factorial, except for I have to divide out what would have been the rest, which is 4 factorial. Okay, so that much we can derive. So that's the permutations. Now we just have one more step. So we've got our 6 people. Now we just have to divide out the ways to rearrange them. But we know how to arrange 6 people, right? If we have 6 people to choose from, and we're rearranging all 6, our first choice has 6 choices. Our second one has 5, 4, 3, 2, and 1. So actually arranging 6 things is just 6 factorial.
How'd you go from 10 to 6? I didn't catch
6
that.
people at a time.
If you hang on, I'll be telling you again. Okay? So this is the number of ways. So this is after I chose 6 out of the 10 people in order. This is the number of ways to rearrange my 6 people. So we have to sort of undo the arrangement. We arranged them, now we have to undo the arrangement, so we're going to divide by this. Because let's do a smaller example just so you can see. So suppose I chose 3 people, right? But my choosing would have said ABC. It would have also counted BAC as a different thing, and CAB as a different one. And how many should I have here? If there's 3, there should be 3 factorial, which is 6 rearrangements. So I should have ACB, and BCA, and CBA. So all of those would have been counted separately in the permutations, right? But I want to consider all of these equal. So I have to divide by 6. Because every time I have a triplet, it's going to be counted 6 times in the permutations. Right, so a combination of 3 things would be counted 6 times in a permutation. So same thing here. A set with 6 elements would be counted 6 factorial times in a permutation. And 6 factorial is 6 times 120, which is 720 times. Right? So now if we go back, what we did first is we did the permutations of 10 things taken 6 at a time. Then we divide by the permutations of 6 things taken 6 at a time. So the combinations of 10 things taken 6 at a time is a sequence of things. First you do it in order, and then you divide out the arrangements. And after you get used to these, you'll already know that the formula for P10(6) is going to be 10 factorial over 10 minus 6 factorial. And that P66 is just 6 factorial. So if you choose all of something, so if I have PNN, that's always n factorial. So finally, this ends up being 10 factorial all over 10 minus 6 factorial times 6 factorial. And that's just moving that top denominator down to the bottom, so we don't get confused about what to do with it. So if I pick 6 things out of a set, that's kind of equivalent to picking out 4, isn't it? Out of this set of 10. Because 4 is the other 4 are the complement, right?
Yeah.
So it should be the same number of ways to choose 6 things as there are 4. Because choosing all the ways to choose 6 things is exactly equal to all the ways to choose 4. Because every time I choose 6, that's equivalent to not choosing those 4 that were left. Does everybody see that? So if I choose the numbers 1 through 6, that's the same as excluding 7 to 10. So I'm asking you to believe this, and then we're going to prove that C10.6 is equal to C10.4. Because every one of these sets corresponds to every one of those. I can match them up. Right? So if I had 1, 2, 3, 4, 5, 6, that would match up with 7, 8, 9, and 10. If I had 1, 3, 4, 5, 6, 7, that matches up with 2, 8, 9, and 10. So if I were counting these sets, counting this set is the same as counting that one. But if you go back and look at the formula we just got, you can also see from the formula, let me put that back up. What is this number right here? 4 factorial. So let's write these formulas again for both of them. So for C10.6, we ended up with 10 factorial on the top, 4 factorial, 6 factorial on the bottom. Let's do C10.4. That would be P10.4 over P4.4. Right? Because I would take a permutation of 10 things taken 4 at a time, and then I would rearrange the 4 and divide by that. But remember that for 4 at a time, it's 10 factorial over 10 minus 4 factorial. And 4 things rearranged is 4 factorial. And this ends up being 10 factorial over 6 factorial, 4 factorial. And that's why they end up being the same, because multiplication in multiplication order doesn't matter, right? So 4 factorial, 6 factorial is the same as 6 factorial, 4 factorial, and that's why the combinations are the same. But the fact that they match up, that's the real reason why they're the same. The formula comes out because it's a good formula. The real reason why it's the same is that picking 6 is the complement of picking 4. So anytime I have a number, so if I have CNK, that's going to be equal to CNN minus K. Right? So as long as these bottom numbers add up to the top numbers, those will be equal. Okay, so we just talked about combinations. Was that with or without replacement? That was without replacement. So the normal permutations and combinations where you see them written like this or this. Let me make these K's because actually they're easier to read and tell apart from the R's if I get a little bit sloppy. Okay? So these are without replacement. If you ever see these formulas, this means without replacement. So that's just something that people assume. If you tell a mathematician to calculate this number, they're going to assume you mean without replacement. And your calculator assumes that too. So if we have a problem that uses the product rule, you know, like how many rooms are there if I have 30 floors and 5 rooms per floor, that's a permutation. But I don't count it that way. I just figure out, that's not a permutation. I meant the strings with, you know, out of the letters A to Z. That's a permutation because a string always has order mattering, right? If you don't know that, strings are like arrays and order matters. So the first element's different than the second, and I care which one is which. Okay, so any string problem with replacement, that's a permutation, but you usually just figure out what's your alphabet size and raise that to the number of letters in your string. So the only thing we have left is combinations with replacement, right? So we haven't done that yet. All of these are without replacement. Then we had a permutation with replacement. And the only thing left is combinations with replacement. And the reason why it comes last is because it's the hardest. But they're the most fun problems to solve. Actually, the hardest is when you have combinations of these, where you do one thing and another, and you actually read the problem and you don't even know which one it is yet, because you actually have to break the problem into parts and figure out each part. And we'll do some of those later. But first, let's learn about combinations with replacement. So here's an example, which happens to be on page 4 of your notes. You have 4 kinds of cookies. And you're at a bakery. So how many ways are there to choose 6 cookies? Now, first of all, a little alarm might be going off in your head to say, wait, I'm only choosing from 4. How do I get 6 cookies out of that? I can have 2 of one kind, right? So that's why this is a with replacement problem. It's a combination because, as far as I'm concerned, the order of the cookies doesn't matter. Okay? So this is a combination with replacement because order doesn't matter, and we're allowed to have more than one of the same kind of cookie. So you have these questions you ask yourself. Does order matter? Yes or no? In this case, no. Is there replacement? Yes or no? In this case, yes. So we have a combination with replacement. Now we have to figure out how to solve this problem. So let's figure out, let's just number our kinds of cookies 1 up to 4. And just try some solutions. Has anybody got any ideas?
6 ones.
6 of one kind.
Okay, I could start listing all the ways to count to get them, right? So I could have 6 of one kind, right? So I could have 1s. Okay, that's all the ways to have 6 of one kind. Okay, now what?
5 of one kind and 6 of one.
5 of one kind and 1 of another. Okay. Are you starting to see why this is kind of a hard problem? So I could do 5 of one kind and 1 of another. And so on. But do we really want to do this?
Not at all.
No. We don't want to do this at all. So there's lots of ways I could do this problem. I could say, what did I choose first? What did I choose second? What did I choose third? And I could try to divide out order. But that, again, is not going to work in this case. Okay, so this is going to be another problem that we map into a binary string. Why is it good to map things to binary strings?
Only 2 ways of choosing.
It's easy to count how many there are that look a certain way, right? That's why. That's the only reason why. It's easy to tell if 2 of them are different, and it's easy to count them. So what we're going to do is make an order form. How many people have gone to Char Grill? Have an order form, right? You have little blanks and you draw numbers in them. Now, assuming that, a computer was reading these, they wouldn't even have to read the labels, right? It would just have to know which blank it was in and whether there was a number in it or not. So what I would do on this order form is I would have spaces for my 4 kinds. And then I would ask people to just draw lines if they wanted cookies, or actually circles, because cookies are round. Okay? So if they want 6 cookies, they just have to put 6 round circles on here somewhere. Say I don't like cookie number 4. Actually, any way you spread them around, it's going to be a unique order, right? As long as if I put the same number of zeros in the same boxes, then it's going to be the same. If I have a different number of zeros in 2 boxes, that's going to be a different order, right? So is everybody convinced that this is going to represent our problem well? Like if you work at the cookie shop, are you ever going to be confused about how many to give anybody? No, you know the total number of cookies to give out and how many of each kind, right? So now all we have to do is figure out how many different ways there are to fill out this slip. Okay? So we partially converted it to a binary string, right? We have the cookies are zeros now. Now, the only thing left is we don't need these ends. We don't actually have to consider the ends of the paper. You can see where they are, the ends of the strings. So all we have to do is figure out how many of these sort of dividers are there. So I like to call these divider problems because I end up mapping them to problems with dividers. Now after I circle them, they kind of look like ones in the middle. So let's put ones for the dividers. So this string happens to be 001, 001, 001. So everything up to the first divider is how many of the first kind I get. Everything up to the second divider is how many of the second kind I get. Everything up to the third divider is how many of the third kind I get. And everything after that is how many of the fourth kind. So now every possible selection is now a binary string. So somebody give me like numbers of cookies they might want. Like what's your order? Donna, what's your order?
2 of the 2s and 2 of the 3s and 2 of the 4s.
So she wants 2 of each of those. So there's my string for Donna's order. She wants 2 of kind 2 because there's none of kind 1, 2 of kind 2, 2 of kind 3, and 2 of kind 4. So now anytime anybody gives me a binary string, what do the binary strings have to look like for them to be valid orders?
Has to have at least
6.
They have to have exactly how many what?
3 ones.
They have to have
6 zeros.
exactly 3 ones and exactly 6 zeros if I want to order 6 cookies and I have 4 kinds. So if we look back at our order form, we had to put a certain number of dividers to divide all the kinds. So you know when you're making columns on your paper, how many dividers do you have to put to divide up all your columns?
1 less than.
1 less than column.
1 less than the number of categories or columns that you have. So our ones will be the dividers, and there will be 1 less than the number of kinds. So a 1 is a divider, and the number of dividers is kinds minus 1. And then zeros are my items. And the number of zeros is simply the number of things that I want to get. So that's the number of choices that I want to make. If you're sort of thinking about the other way to do problems, or the number of items that you choose. So now we just have to count up how many binary strings are there that have exactly 6 zeros and exactly 3 ones. So order matters in this case because it's a string, right? And the order that you put your zeros and ones determines which cookies you get. So we've mapped this to a binary string problem, which is a little bit easier to solve. So now what I do to solve this problem is I think, okay, I have 9 total characters, right? So I'm going to draw places for 9. Because all of my solutions have 9 blanks. And then I have to choose out of these 9. The blanks are a little deceiving because actually all I have to do is choose which ones are going to be 1s or which ones are going to be 0s. Right? So I can put these numbers in a hat. Now I choose, let me just choose which ones are dividers. So that means I have 9 things in my hat, and I don't care what order I choose them because I'm going to put a 1 in whatever numbers that I choose. I have 3 dividers, so I'm going to choose 3 of those. And now we've mapped it into a problem we know how to solve. We have a formula for this. It's the mapping that you have to do that can be confusing. So if you have your notes here, I'd like you to get them out.
Where does 9 come from?
I'll talk about it in just a second. I'll talk about it again. So if you get out your notes, if you don't have them, I'm going to show them right here, but be sure to look at them later. There's a table on page 6 for solving. It's sort of a summary of permutations and combinations. And if it's hard to read the exclamation points on there, please, correct anything in your notes from your handwritten notes from class, because sometimes these factorials print out funny for some reason. Okay, so this table says, does order matter? Does it have replacement or not? What's the symbol for it? So all of this is put in here. The thing is I don't really want you to use this table for divider problems. Okay, so the problem that we just did, a combination with replacement, I don't want you to think of it in the same category as these things. Because if you notice this and this, you're going to mix those up if you just memorize this table. If you know these 2 things, and actually you can derive this one from this one, you can actually derive everything in this table, then you can use this formula whenever you solve a divider problem. So I want you to separate divider problems from this formula over here. And that's why I bring out this table, because I really don't want you to use it. It's in here because a lot of people like to have it so they can sort of separate stuff. Does order matter or not? So feel free to use this part of the table to help you remember which one's which or whatever. But when you do a divider problem, I want you to think about the dividers, think about the binary strings that you're converting to, and then solve the problem. Because I guarantee you will mix up these numbers on the bottom, and it will be wrong as soon as you mix them up. Because you won't know what n is in this problem, and you won't know what r is. And then you'll forget which one to subtract 1 from. Unless you know which ones are the dividers and which ones are the things. And if you solve it that way, you won't have any problem. So please don't use this part of the table. The rest of the table is great. It's fine. But I want you to solve divider problems just the way we just did. So let me go back over that. Because it was kind of a long mapping, right? Kind of did a lot of stuff. But after you get used to it, you'll know what to do every time. So we mapped our problem to a binary string. We made an order ticket, is what we did. We had to put columns for the number of kinds. We had to put dividers for the number of kinds. So 1 less divider for the kinds, and then we put zeros wherever we wanted items. So the total number of things on our pieces of paper, like however many marks there are on there, that's how many choices I get to make from. So how many things were there? 1, 2, 3, 4, 5, 6, 7, 8, 9. Because there were 3 dividers and 6 objects. So if you add the dividers and objects, you have the total number of things that you want to choose from. And here's my picture of that. I had 6 zeros and 3 ones. And these are the dividers. And that's number of kinds minus 1.
You divide that, or you add that? 6 and 3 get you 9.
For the total number of items.
Right, for down here.
This is 9. I'm adding.
Yeah, okay.
I'm not
I
dividing.
thought you said divide.
No, these are dividers.
Okay.
I'm not doing any division in this problem. case because I'm making a binary string. I have to make places for the zeros. I have to make places for the dividers. There has to be enough room on your order slip for people to write however many things they want. And you have to have enough columns for how many kinds you have in your bakery or whatever you have. So out of those total number of marks that are going to go on the paper, you have to choose how many are zeros or how many are ones. Because remember that if the bottom two numbers add up to the top number, those are equal. I can either choose the zeros or the ones. It doesn't matter. I like to choose the dividers because usually there's a lot less dividers than there are things that I'm choosing. You know, because I go to the donut shop and they have like 20-some kinds. I'm not going to get 20 donuts. I'm going to get like 12. Unless I'm feeding my brother, and then you never know. Just give me 2 of each. Okay, so let me write down a general formula for this. So you can easily look at something to see if it's a divider problem. Now, who can tell me what kind of words to look for in a divider problem? I won't see the word divider in a divider problem. That's a problem, right? I'm going to see the word kind, or category, or type. Whenever there's multiple items of something and I can have more than one of them, then that's a combination with replacement problem. And another hint is most of the time when I make up one of these problems, it has to do with donuts, cookies, or M&Ms. So a lot of times it also has to do with because I can't tell the difference between things. So of course the order doesn't matter. I don't care if I got the first chocolate chip cookie or the 10th chocolate chip cookie or whatever, because the order usually doesn't matter. So if I have some things I can't tell apart, a lot of times it's going to be a divider problem. Or at least part of it's going to be a divider problem. So we're going to have multi-stage problems also, where you're going to have to do different things. So we'll do that. But if you see the word kind, category, or if they're items you can't tell apart.
Indistinguishable.
That's right, indistinguishable items. That's what this word means. Indistinguishable. That's a hint. It may not be a divider problem just because there's indistinguishable objects, but a lot of times it's going to be. If you can figure out what the kinds are, then it's often going to be a divider problem. So then the solution, once you figure out you have a divider problem, is your total number of choices will be the dividers plus the kinds. That's how many marks would go in your order form. And you can choose the kinds or you can choose the dividers. Sorry, not kinds. Items. Dividers and items. That's number, things you're going to take home with you. And you can choose the items. Or you can choose the dividers. It doesn't matter which one you do because they are equal. Sorry about that. Dividers and kinds shouldn't be there twice, right? Because dividers depends on kinds. The dividers is one less than kinds. And that's why I didn't want you to use the table, because the N and R are so confusing when it comes to kinds and dividers and what you're taking home. Like, so weird. Because normally you think the set I'm choosing from has to be bigger than the set I'm taking home. And a lot of times you have fewer kinds, or you don't actually have more kinds than you're taking home, or vice versa. So it's kind of confusing. You can't use that less than relationship to help you figure out which one's which. So you figure out what the kinds are, you subtract when you get the dividers, and then you use this formula. So here's another example that's on page 6 of your notes. I have 12 identical flyers to place in 4 mailboxes. How many ways can I do it? And we assume we're going to distribute all of the flyers. Now this is a deceptive problem because it doesn't have kinds or categories.
It does have identical.
But it does have identical. So we have to sort of figure out what's the map in this problem. So how would I draw my binary string for this? Can I think of anything in this problem as a category?
What mailbox you put it in?
Which mailbox? So the mailbox that I'm in has all, everything that's in it would be identical, but the mailboxes I can tell apart. So the things I can tell apart are the kinds, and the things I can't tell apart are the items. So kinds is mailboxes. So how many dividers are there?
3.
That's right, dividers, there are 3 of them. And there are how many items? 12. So the solution to this problem is 12 plus combinations, 12 plus 3, choose 3 of them, or choose 12 of them.
And since we can just recognize that as we're reading through the problem, that could be the answer on the test, just right out
Absolutely.
right
This is a correct answer.
there. Cool.
Now, I would definitely put this, just in case you misread something and just wrote down the wrong number here, just so I know that you knew what the kinds were and how many dividers there were in the items. Then maybe you might have just written something wrong. Like, you can put this as your answer, but you better be darn sure that you double check it. And make sure that, because sometimes you might actually just write down a 2 when you really knew there were 3 dividers, but you're just taking a test and you write down 2 anyway.
12 instead of 15.
Right. If you write this is a wrong answer. Right? Because I'm not choosing 3 out of the 12 flyers to do something with. Instead, I have like an order form that tells me where to put the flyers, and it has 15 marks on the paper. 3 of them are going to be 1s, the rest will be 0s, and the 0s will tell me how many flyers to put in each mailbox. So in this case, in these kinds of problems, we can't tell the difference between the items in a category. Once they're put in a category, we can't tell the difference between them, but we can tell the difference between the categories. So you could imagine also a problem where you couldn't tell the difference between any of the categories, but we're not going to do that problem right now because I don't want to confuse you. But in this case, I'm trying to tell you another cue or clue for these kind of problems is I have one thing I can tell apart and one thing I can't. Right? I can't tell the flyers apart, but I can tell the mailboxes apart. So that's a clue that this is a divider problem. And I will need to divide the things I can't tell apart, I'll have to divide them among the things that I can. So we'll do some more complex problems of these like these next time. But what I'd like you to do is take a look through your notes and the examples before we come to class next time. I might go over a few of those, especially if you have questions on them. But also I'll do some other examples of counting problems that have multiple stages in them. But right now I want to introduce one more new concept. It'll be the last new thing in counting, so we can do some more problems with it next time. So we were just talking about placing 12 flyers in 4 mailboxes. And instead of counting how many ways there are to distribute the flyers, let's figure out if we can prove that a certain number of flyers gets put in one mailbox. If I have to give out all 12 of them, there's going to be at least one mailbox that has at least 3 flyers in it. Right?
Can't you have 0 in a mailbox?
I could, but I have to be able to, I can show that there always has to be one with at least 3 in it. Because if there isn't, then I can't even put all of them out, right?
Right.
Because if all of them had less than 3, then all of them would just have 2, and I can only put out 8 flyers. Right? So That's a there exists. Keeps coming back to haunt you. So the pigeonhole principle helps me figure this out. And in a minute, I'll tell you exactly what the pigeonhole principle is. But 12 over 4, the ceiling of that is 3. Because 12 over 4 is 3. I don't need to round it up anyway. It's just 3. So I can guarantee that there's at least one mailbox with at least 3 items in it. And if there were 13 flyers, I could guarantee that there were 4 in one of them. Because I have to round up. And the reason for that is if I did put 3 in every single one of them, if I think of the even distribution, then there has to be 12 flyers. Like, I could put 3 in every one, but I couldn't get 13 in there if I wasn't allowed to put more than 3. So I can guarantee that one of them has at least 4. It's still allowed to put all 13 or 12 or however many in one mailbox. But that's the one that has at least 4, right? So let's do a little bit simpler problem. So what this comes from is pigeons and pigeonholes. That's why it's called the pigeonhole principle. So if you have pigeonholes, that's where pigeons live. So say I just have 3 of them, but I've got 4 pigeons to put in the pigeonholes. I can guarantee that one of the pigeonholes has at least how many pigeons in it? 2, because otherwise I can't fit them all in there. So the pigeonhole principle says if I have n pigeons and k pigeonholes, then there exists a pigeonhole with at least the ceiling of n over k pigeons. So in this problem, I had 4 pigeons and 3 holes. Since I have more pigeons than holes, there's definitely 2 in one of the holes. This is sort of the mathematical way to figure out that that's 2. Since n is bigger than k, there's at least 2 in one of the holes. Because I have to distribute all n of them, and I don't have n boxes to put them in. So this is a good party trick.
What parties do you go to?
Come on, I'm a math geek. It's a great party trick. All the people at parties I go to are mathematicians. I'm just kidding. People who are not mathematicians love these because they never believe you. Okay? So how many, this principle helps me figure out how many people have to be at a party to guarantee that 2 were born in the same month. 13, right? Because I have to have more pigeons than holes. So the holes are the months. And if I want 2 in the same one, there have to be more pigeons than holes. So there have to be 13 people at the party to guarantee that 2 of them have a birthday in the same month. And you know that that's going to happen. So when 2 people at a party go, oh, I was born in August. Oh, you were born in August too. You're like, okay, at least one pair of the people in there has to have that happen if you have 13 people or more. Right? Okay, so that was an introduction to the pigeonhole principle. We'll do some more with this next time and some other more complicated counting examples. See you next time.